These are longer conservation of energy problems. Now, you have this big equation at the bottom of your equation sheet. Let me just write a version of it. K1 plus EPE1 plus GPE1 plus work due to an outside force. That force could be a force that adds energy or a force that takes energy out of the system. So I'll say that's positive work, and this would be negative work, friction. Really, that's always going to be negative because work to the friction is negative. That equals KE2 plus EPE2 plus GPE2. 2 meaning final, 1 meaning original. Now this happens in a transition from the beginning and the end, but I put it on the left side of the equation. So let's look at this problem. Number 1. Okay, we have a bike at the beginning. He's at the top of a hill. If you have an H, you have GPE. If you're moving, you have KE. Okay, there's no spring, so there's no spring potential energy. Now, I should have said to you he's coasting down there. He's not pedaling. So he's coasting down this hill. So there's no work due to it, a force that's adding energy to the bike except for the gravity, but that's taken care of in the GPE. Gravity is already taken care of. There's no average drag. Okay, we have drag on the bike, so we have work due to friction. Okay, at the end, he's not at any height at the bottom of the hill, so, but he's moving fast, so we have KE2. So you can see in this major equation up here, this huge equation, I just select what pertains to the problem. Okay, that's the most important step right there. I have some questions where you just give me that version that's applicable of the conservation law and conservation energy law. Okay, I just did that here. Okay, so let's now just change it, break it down. MGH plus mv squared over 2 minus, okay, that'd be little friction times distance, or drag times distance equals mv squared 2 final speed over 2. Okay, the m's do not cancel out, so I had to put them in. 60 kilograms, 60 times g is 10, acceleration due to gravity, h1 is 40, plus 60 is the mass, times the speed at the beginning is 15 squared, divided by 2, minus the friction. The drag is 70 times the distance, 250, equals, okay, m is 60. I'm looking for a speed at the bottom, right? Speed at the bottom. So v squared over 2. So I do this on my calculator. 60 times 10 times 40 plus 60 times 15 squared over 2 minus 70 times 250 divided by 30 equals. Then I take the square root of that answer because that would give me v squared. I'm not showing you all the steps. So v would come out to 21 meters per second. He's going at the bottom of that hill. Number 2, we got a football. The guy's going to kick the football. Football is like a really rigid spring. So the guy's foot's going to dent the football in like that. And the amount that it denses is 4 centimeters, which is 0.04 meters, which you would need to convert to 0.04 meters. Okay, spring constant is what I'm looking for. I'm looking for the spring constant. So football is caught at a height from where it was delivered off the ground of 2 meters. Okay? And it's not really, it's contacting the receiver's hand. He hasn't stopped it yet. So it's just at the point of touching the hand. I would say this in text. I'm just not typing out everything here. Okay, so at the beginning, what kind of energy do we have? Kinetic? No, it's not moving. It's the foot has hit it, but it's not springing off the foot yet. So there's no kinetic. Is it gravitational potential energy? I'm using this equation up at the top here. No, it's not off the ground yet. Is it spring potential energy? Heck yes. It will. It has a lot of energy, and it's going to spring off that guy's foot. So EPE1. Is any work being done on it? Well, yeah, but it's already been done by compressing the ball. So that's before the first stage. So the foot is applying a force, but it's already compressed the ball. Now the ball's going to spring off the next moment, but it's not moving yet. It's just at that point where it's all compressed, ready to come off his toe. So I don't have any work due to a force. Is there any drag? I didn't mention it, so you can assume there isn't. So EPE1 equals, there's no drag or friction, so you can skip the work due to friction. Okay, the ball has kinetic energy at the end. It also has GPE because it's off the ground. And I forgot to tell you the speed of the ball right before it hits his hand. I forgot to tell you. Let's say it's moving at 40 meters per second. Right before he touches it. I should have told you that. I couldn't solve this without that, so I should have written that. So let's expand this equation. This is KD squared over 2 equals MV squared over 2 plus MGH. Okay, so K is what I'm looking for. So K times the distance it got compressed, 0.04 meters, divided by, well, that's squared, D squared, divided by 2 equals the mass of the ball. Don't use grams, use kilograms by dividing by 1,000. Don't use grams. Times the speed it had right before he caught it, squared over 2. I'm just following these equations up on the line above it, plus 0.430 times 10 times the height off the ground, 2. So let's solve for K. So what I did was 0.430 times 40 squared divided by 2 equals plus 0.430 times 10 times 2 equals times 2 to get rid of the 2 on this side, divide by 0.04 squared to get rid of the 0.04 squared on the top here. That equals K. And so I get it equals 40. I'm going to round it up to 440,000 newtons per meter. Footballs are really stiff. Okay? So 440,000. I rounded it up to two places. Okay, now that's the second one. Now this one, let's do the same thing. I'm running out of space here. Okay, so we have a bullet that isn't even shot yet. Okay, the zero reference line, 0 GPE, is where the bullet starts. I'm going to shoot it into a tree. It makes a hole in the tree, and it gets caught in the tree. It sinks in the tree 5 centimeters. So, let me ask you this instead of what I'm asking here. What force does the tree apply to the bullet to stop it? Okay, I should say what average force. So the tree's going to apply a force so the bullet doesn't go all the way through the tree. Okay, so I'm going to say the force of the bullet. The force on a bullet, let's say, is 8,000 newtons. Okay, so let's solve that problem using conservation of energy principles. Okay, so what kind of energy do I have at the beginning? Potential? Gravitational potential? No. It's the lowest. It's at the zero reference line. Kinetic energy? It hasn't been shot yet. Spring potential energy? I see no springs. So basically, sorry, I'm going to have to start down here. So we have zero energy. Okay, is there a force that's going to be pushing it in between this first picture and where the bullet stops in the tree? Yes. There's going to be work due to the explosion of the gunpowder behind the bullet in the rifle. Is there going to be a force to stop it? Yeah. Or slow it down? Yes. Well, let's make that negative because work due to friction or drag or normal force in this case of the tree pushing it, resisting its motion through it. That's always negative work. Okay, that would equal only potential energy at the end because it has stopped. So break this up. So let's put it here. So breaking this up, 0 plus work to the force is big F behind the bullet times the distance that it pushed, that force pushed the bullet. Now, the force of the bullet is only exerted on it when it's in the barrel of the gun being shot. Once it leaves the barrel, those gases aren't behind it pushing it forward anymore. So let's just put in our numbers. 8,000 times the distance it travels is 90 centimeters, which you have to change to meters. So minus the work due to friction. Okay, well, I don't know what that force of friction is, but I know that the distance that it pushed in the tree was 5 centimeters, which I will change to meters. Okay, so that's minus F times D. This is the other D. Okay, that equals mgh. So the mass of the bullet is squished down here, 250 grams, but I had to change that to kilograms times, divide by 1,000 times 10 times the height of the tree from the ground from where it was shot is 47 meters. So let's solve for this. So I'm going to take, let's change the color. I'm going to take 0.250 times 10 times 47 okay, and then I'm going to equal that. And then I'm going to subtract this. So subtracting 8,000, oops. $8,000 times 0.9. Okay? So I'm getting a negative answer. Then I'm going to divide by 0.05 to isolate the F. So I'm getting negative F equals negative 0.50 newtons. Okay, so that's the force that the tree stopped the bullet with. Okay, so the negatives would cancel out, so I probably would round that 1205. I'd probably just round it to 12K. Okay. Alrighty. Final question. Okay, so let's use the law of conservation of energy again. At the beginning, does the guy have kinetic energy? The bike, yes. So KE1, does it have GPE? No. He's not off the ground at the beginning right here. Does he have SEPE? No. No spring. Okay, so we have plus work to the... Okay, do we have work pushing the bike? Do we have work pushing the bike? Yeah, he's pedaling. I should have reminded you. And that's what I'm looking for, the pedal force. What's the pedal force? Well, if we have a pedal force as he climbs up the hill, we also have work due to a big F. Is there any drag? Yeah, drag's mentioned. So we have work due to friction as well. Okay, actually that's minus because work due to friction is always going to be minus negative work. So let's do it that way. Okay, this equals, at the end, does he have KE? Yes, he's still moving. He didn't come to rest. That's V. That's V2. That's V1 over here, 7. Okay, does he have height? Yes, so he has GPE. There's no spring potential energy. Okay, break this down. M1 V1 squared over 2 plus FD minus friction D equals MV2 squared over 2. There's only one mass, so let's erase that one. Okay, and then GPE2 obviously is MGH. Okay, plug in your numbers. Okay, so the mass is 35 kilograms. I don't got to change that. 35 times 7 squared over 2 plus the the force, the pedal force is what I'm looking for. So I'll keep that as F. The distance that he pedaled was 75 meters up the hill. See, meters, I don't have to change it. Minus the friction, the drag is 70 newtons. And again, that's over 75 meters that drag happened between the beginning and end. Okay, that equals the mass, 35. The final speed was 2.5. He lost a lot of speed. Over 2 plus 35 again times G times H. How high did he get? 33 meters. Okay, so we're solving for V. I'm sorry, we're solving for F, so let's calculate all this first. 35 times 2.5 squared divided by 2 plus 350 times 33 equals. Okay, I'm getting this big number here. Okay, and then let's subtract this guy. Minus 35 times 49 divided by 2 equals. Then let's add this guy, because I have to get rid of it. So add that to both sides. Plus 70 times 75. Get a big number there. Okay, that leaves F times 75. So let's divide both sides by 75. So I get 204. So the pedal force is 204 newtons. The pedal force. Okay, let's erase that P. Okay, so that's how much force he applied during that section of climbing the hill. That's it.